All right, good afternoon. If this is the talk you're looking for, you're in the right place. If not, you're probably just holding the seat for the movie, and I guess I'm glad to be the person to keep you busy while you're waiting. This talk, Ignoring Nulls and 5 Other Horrible Things That Most Developers Do. I'm not saying that you're horrible developers, I'm just saying that we all do it. Also known as the 7 Deadly Sins of Programming. But wait, you might be thinking, because I know some of you aren't going to be able to concentrate on anything else until you know why I said 7 deadly sins when 1 plus 5 is 6. Don't worry, you'll get that soon enough. A little bit of a spoiler, it involves recursion, but not the way you think. So about me, I'm Michael Meadows. I am an architect at Insight Consulting. I focus mostly on cloud-based implementations, cloud-native implementations, but specifically highly regulated and high-volume, high-criticality systems. The reason I do this talk is that I've spent a lot of times really getting down in the guts of systems and finding those little ways that we kill ourselves in our code. So this is actually a combination of several different talks that I do, and I try to cram it all into one. And I'll tell you right now, in all of my run-throughs, I have not gotten it under an hour, so we're gonna get right this time. Also, aspirational sea kayaker. That doesn't mean that I actually do sea kayaking. It means that I wish I could do sea kayaking. I go like on 2-foot swells, but that's about as far as I go. So for those of you, especially you functional programming dogma people looking for validation, and I'm going to turn off the captions, that it's not really working because I don't have network. I'm not here to validate your feelings about functional programming. It's going to sound like I'm here to validate your feelings about functional programming because a lot of the things I talk about are addressed in functional programming. But if you want to spend an hour with me debating why we shouldn't do functional programming, I can also do that. All right, so the deadly, oh, no, see, not yet. First, we have to talk about why do we do these things, right? Like if I'm saying you're not a bad developer, why do we do these bad things? There's really 2 reasons. First is what I call language-driven bad practices. And by language, I mean really language, framework, SDK. The environment that you're working in, the thing that makes you productive in building code also nudges you in certain directions. Sometimes they're good, sometimes they're bad. I'm really going to focus on 3 of the bad ones. And then the second is high mental load. And what I mean by this is if we thought about it enough, we would realize that we're doing this wrong. But thinking about it enough isn't really something that we want to do. It's like these 3 things that I'm going to talk about here are kind of icky, and we don't really want to spend a lot of time thinking about them. So we just kind of let it slide. All right, so the 7 deadly sins as promised. Under language-driven practices, I have misusing exceptions. And I know in the abstract I said boxing and unboxing of objects, but it really just sounded like I was picking on Java, which I will proceed to go ahead and do. But I wanted to throw in a few other things as well. So I'm going to say underestimating the impacts of objects on memory management. And then everything related to strings, like the whole kit and caboodle as far as strings are concerned. And then under high mental load, ignoring the complexity of null, trying to simplify date time, and if you've ever had to deal with date time problems, you probably know what I'm talking about here. And then everything related to logging. And then the 7th one is being dogmatic about anything that I say here. When the perspective that I'm bringing to this is really around hyper-optimization. But knowing these things can kind of keep you from getting into this trouble in the first place, right? The reason that this involves recursion, by the way, is that the 7 deadly sins are a dogma, and I'm telling you not to be dogmatic. Nobody really chuckled when they got that, so I'm assuming not very many people spent too much time in Catholic school making dogma jokes. All right, so moving on to the first category, language-driven bad practices. Oh, and by the way, let me go back to this slide. I did use AI-generated art in this, and you can usually tell by the hands. So I specifically, and this is a relevant slide. This is Guernica by Picasso. Chose this one because he also really doesn't know how to do hands. Okay, so exceptions are your enemies. except when you follow my advice. So what is an exception? An exception really is your escape route, right? If you think about what an exception does, it basically allows you to stop whatever's happening, break all of your control structures, and then go do something else, right? And that something else usually means escaping. So they're super powerful, but they're also super dangerous because it's really hard to reason about something that's not following the rules of the control structures, right? So if you're in the method that throws the exception, you can reason about that. Maybe if you're on the next one out, you can reason about that. But if you aren't careful, exceptions can really make it hard for future developers to figure out what the heck is going on. So we have to be careful about it. Most languages have built-in signaling and filtering for exceptions, which makes it easier to deal with. We just have to understand how to use those correctly. So a little bit of background. HCF is an assembler or assembly mnemonic, and it stands for halt and catch fire. And you know, it's a good mnemonic in that that's essentially what it did, right? If you were writing an assembly program and you detected something that was so wrong that it could possibly damage your hardware, you issued an HCF, and usually what that told the CPU to do is just give up, right? And by give up, that means you probably have to restart the system in order to get it working again, right? In my mind, I kind of think of exceptions like that, right? Any Ren and Stimpy fans, you know what I'm talking about. So how we do it wrong is that we often use exceptions in non-exceptional flows. And what I mean by that is if we can figure out another way to solve this problem with existing control structures, we probably should. If an exception is coming from an external service and we can figure out how to solve it within our regular control structures, we should. The reason for that is that it just makes it easier to understand what's happening in your code, right? Again, exceptions don't follow the rules, and they do that for a reason. Reliance on the message. So most exceptions have a free-form string called message that lets you put plain language, whatever language it is that you speak in there, for somebody to read. I wish they wouldn't do that, right? An exception should be descriptive by its type and by its data. The message itself, we should never use. It only leads to heartache. Catch, log, throw. I know every single person in this room is guilty of this. And then swallowing a whole. There are times when you have to do this, but we should try to avoid it at all costs. And then the final one, and this one's a little subtle, is as a substitution for a return value. I'm not going to spend too much time on this one. Well, actually I am, because it's in the next example. But this overlaps a lot with null. So kind of hold this. There's a little bit of symmetry between the language-driven bad practices and the high mental load bad practices. And notice I try to avoid the converse term or inverse term of best practice. I'm going to tell you what's bad, and I'm going to tell you what's better, but not what's best. In a lot of cases, I'm also going to tell you you should defer to the language framework or runtime that you're using to determine what's best. So the first language I'm going to pick on is JavaScript. And this code is pretty relatively straightforward, right? We're looking at it. There's not a lot of lines of code. It does something stupid, which is it takes an array of strings, and it returns the last string before null, right? So if there is no null, then it just returns the last string. If there is a null, it returns a string before that. And if it starts with null, then it throws an exception. So if we look at this format value method, it's okay, right? Like it throws an exception, which is okay because it doesn't know how to handle value not having a value. But then we go out and look at how find is using this, and we see that we're abusing try-catch here to create our own control structure, which is that if we hit that null, we just want to stop, right? We want to stop, and then we want to check to see if we already have a value, and if we do, we'll return that. Otherwise, we throw that same error. The problem with this is what you're looking at is 10 lines of code, and you can figure out what's happening. But everybody knows that like when you run into this problem, it isn't 10 lines of code. It's like one 500-line method that is being called by 28 other 500-line methods, right? And in that case, it becomes really difficult to figure out what's happening. We're not following, we've externalized that business logic to something that isn't under our control. And so, I mean, this is a very simplistic example, but I tried to roll a few things in here to show, how this innocuous code can cause problems in the future. A less bad example is this one where, that format value could still throw an exception if we want. That's fine, but we've just moved it into a check. So when we talk about what we should be doing in terms of exceptions is just the answer is avoiding them, right? Even if they're there, we should avoid them at all costs. Even if we know that format value is checking for null, we shouldn't rely on that for our business logic. We should treat it as it is an exception. And if it is an exception, we don't want it to occur. So how do we do it right? I would assert that there's only 2 times when we can handle an exception. The first time is as soon as possible. So we catch the exception if we know what to do with it, and then we bring it back into our normal programming control structures. If we can't do that, then we wait till the last chance. And what I mean here by last chance is we really, like whatever it is, like if it's a web framework, it's basically where that web request came in, right? Let it bubble back up there, log it, you don't know what to do with it, and move on, right? And we should use exceptions to indicate to the program, whether it's ours or something else that's using our code, that something happened and we cannot, like it's not within the bounds of the business logic that we're writing, right? We don't know what to do with it. Here's an exception. If you know what to do, great. If not, it's an error, right? That's it. Like we should not overcomplicate exceptions beyond that. Somebody's calling me. Do we have any questions on that, on exceptions? No? Okay. And I forgot to mention, if you do have questions, this bit.ly, I haven't seen a bit.ly link in a long, long time. Takes you to Discord. You can add, there's a forum for this talk. You can throw them in there. All right, so objects. Let's talk about objects in memory management. And again, this is, I can hear my former functional programming language coworkers already, exuding their superiority over me. Objects are useful. They're not horrible, but if we're not careful, they can burn us. So I'm going to start with some quotes. And the only reason really I have these quotes is the top one and the bottom one, but the middle 2 are interesting. Everything is an object, said Java in 1996. I don't know if that was actually said in those orders, but I've heard that before, right? And it burns me for when it comes to optimizing your code. Object-oriented, this one's just funny. Object-oriented programming offers a sustainable way to write spaghetti code. It lets you accrete programs as a series of patches. And then Alan Kay, who actually did invent the term object-oriented, the practices were there in protoform before that, said, actually I made up the term object-oriented, and I can tell you I did not have C++ in mind. And this last one really is my favorite one because it has applied to me more than once. It's Fowler's law, so this is from No More Hacks. Fowler's law is invoked when you have a penetrating insight into object-oriented programming. If the quality of your insight is very high, you realize that Martin Fowler published the idea only 5 years ago. And if it's poor, you realize that he published it more than 10 years ago to demonstrate how many people still don't get it. If you don't know who Martin Fowler is, he's an Agile and architecture hero. He's written a number of really great books on architecture. All right, so when should you not listen to what I'm saying here? And the answer is going to be really like if you don't need to. And that's really kind of a broad answer. But the way that we work with objects in whatever language it is that you're using is designed to be as intuitive as possible. And really, when you start to deviate from that, they're hyper-optimizations, right? Don't veer off into hyper-optimization because you're gonna sacrifice the readability and maintainability of your code for performance issues that may not ever happen, right? But when you start to go down that road, if you start to see, like, from a performance perspective, that your heap is just filling up and your garbage collection is running all the time and you're scaling and it's not really helping, well, there's some things you can look at, right? And this was actually a hard section for me to write because, like, every language does this a little different. I am going to be picking on Java, and it's going to sound like I'm going to offer up C# as a healthy alternative. I'm not really. It's just that there happens to be a framework that I like in there. So what exactly is the problem, right? Like, most of us use objects, and they haven't really been a problem, right? And it all really goes back to the olden days where we had to actually manage the memory for objects, right? So most modern frameworks run within 2 memory spaces. There's the stack, which is basically all of the operating memory that's being used for the method execution and the next method that calls and the next method that calls. And then there's the heap where all of your objects lived. So when you created an object in, for example, C++, you had to allocate it, and then you had to remember to deallocate it, because if you didn't, then you would have a memory leak. You don't have to do that anymore, which is super great, right? And on top of that, we have garbage collection, which takes care of cleaning all that stuff up for us, right? But you have a problem, which is that you can still, like, create objects faster than garbage collection can get rid of them. And if you do that, then you end up with pauses. Your program literally just hiccups while garbage collection does its job. And garbage collection is generational, which means that it always goes for the low-hanging fruit first, right? So you could end up with a situation where you're building up these later generations because your objects are living a little bit longer than your garbage collection, and then it has to take a really big pause to get rid of those higher generation objects that have been living for a while, because it has to do more analysis on them. In high-scale systems, in systems that have, thousands to tens of thousands, hundreds of thousands, millions of requests happening or operations happening in very short periods of time, you can watch in a profiler this sort of sawtooth pattern of your memory usage, because you keep creating objects and then destroying them, and creating objects and destroying them, and that has a meaningful impact on your performance. Excuse me. So it's not just memory, it's also CPU, but memory is usually the long pole in this tent. Right? Memory is usually the thing where you just can't scale fast enough. And that has to do with how we are dealing with objects. So some things that you can do. One is to not be afraid to use singletons. There's a caveat here, which is sometimes it's actually better to use stateful objects. And again, I'm going to pick on Java, but really this is the case. Because Java specifically doesn't have value types. So if I'm passing a bunch of primitives over method calls, it still has to turn them into objects. If you use dependency injection, learn how it manages this life cycle of objects and really put some thought into what life cycle you should pick for something that you're injecting and how that impacts the code that you're writing. If your language supports structured value types, and what I mean by this is structs and tuples, then use them when it makes sense. Don't overuse them, but when it makes sense, these are really good things because they don't need to be allocated in the heap, right? They're passed by value. The downside is that when you pass something by value, you're essentially making a copy of it, which means that you can't mutate it because you're not going to get side effects in the things that originally passed it, right? Transient objects should truly be transient. And what I mean by this is if you just create an object for a single purpose and then you're done with it, if you want that thing to be garbage collected, you need to release it as soon as you can, right? Because if you don't, then it moves into the next generation of garbage collection and it becomes much more costly to get rid of. And then understanding the consequences of primitive boxing, and my Java friends out here know exactly what I'm talking about here. And if you want to know more about primitive boxing, this link is tiny, but you can get my slides. I don't know if I showed you the link for that, but I'll put it up at the end. He does a video and has a blog post on the cost of auto boxing, and I think it's really great. So here's my mountain, a pile, a heap of garbage to be collected example. And this is my Java boxing example. So we basically have this very contrived example where we have a method called do this inefficiently, and it takes an int and a Boolean, and then it passes on to get result, that same int Boolean, and then an additional string called Steve. So it looks innocuous, right? Like it's not that sophisticated or complicated, but there's a lot of things happening here, right? When I call do this or do the thing this inefficiently, when I pass that int and that Boolean, they both have to be boxed into objects on the way in and then unboxed back out into primitives on the way out. And then when it calls get result, it has to box them into objects again and then unbox when they come out. In addition, Steve is not a symbolic constant, it's a literal constant. And when we get into the string part, you'll kind of see where this is a problem. But essentially, this could potentially create multiple copies of Steve in the heap that just need to get cleaned up. So even just little tiny bits of code like this, right, could be a problem. And the reason I say don't be afraid to use singletons sometimes isn't the best advice to take is because we tend to write transaction scripts, which are objects that are not stateful, right? And they're not stateful because all they really do is act on the data that we pass into the method. Well, the problem with that here is that actually creates a lot of extra object allocations in the heap, right? So an alternative in this case, and this is a very language-specific alternative, is to make it stateful, right? Like, don't be afraid to make it stateful. So now we have this thing called foo helper, where the Boolean bar and the int foo are its properties, right? And those are passed in when we initialize this thing. And now when we call do inefficiently, all it really does is still has to allocate Steve. If we wanted to make this even more efficient, we would put Steve up at the top as a constant, and then it's only allocated once. But this becomes a much better way to solve this problem than what we had before, right? So in this case, it's not a singleton, right? Like we want this to be a stateful object that has behavior, a POJO, right? And another example, and this is me not picking on Java, but again, you know, like C# just does this a little better. C# supports value types, right? So there is no cost to passing these things by value, except that it just takes up a little bit more stack, right? So in this case, we can do this like a transaction script, and you know, that opens up other, like it's you know, it's debatable as to whether you like this better or you like this better, but what I'm trying to point out is that in one language, one option is a better option from a memory perspective, right? This code, the only thing that gets allocated on the heap in all of this, right, is the foo.toString and then the constant Steve, right? So constant Steve is there, but there's only one copy ever, and foo.toString turns your int into a string. So in this case, like the memory doesn't grow that much as this scales, right? So it really is very, very language dependent. That's the point I was trying to make here. So do we have any questions on this part? No? Okay. All right, strings are objects. So they're also arrays of characters. So all of the problems with objects will copy over to strings, and then we have some new ones too. So I don't think C invented strings, but C gets blamed because most modern languages are the spiritual grandchildren of ANSI C. So in ANSI C, there is no string, right? A string is a bunch of helper methods and some syntactic sugar over arrays of cars. And the first example here, those should be single quotes. I don't know why I made them double quotes, but note that the array is larger than the string itself, and the string is terminated with a \0. Remember, in ANSI C, there are no bounds checking, so you always want to make sure your string's a little bit larger and you have a \0, which is a null character. Otherwise, you could just keep going into other memory and like everything gets really weird. And the syntactic sugar in this case is that you can actually allocate it like we're used to with the double quotes. It's still an array of characters. So knowing that this is still under the hood, right? This is still how strings work. It's just we have a lot of magic happening, right? When we do this in our modern languages, it it optimizes the creation of these things. It tries to optimize the management of them, and tries to optimize the garbage collection of them as best it can, right? It also makes them immutable, and that's both good and bad, right? It's good because we can basically reuse strings and treat them as equal, and that helps a little bit with the heap. But it's bad because we can't mutate strings, which means every time we try, we create a new string. So it's worse, but it's also better, right? I mean, like, I wouldn't give up all of the stuff that I get with the modern treatment of strings to go back to what we had with ANSI-C, but it does hide that from us, right? Which can cause us to do some things that are not that great, right? So what are those things? Well, if you don't have a string builder, you should just probably go find a framework or a language that does, or a framework that does that for you. Transitional states for strings just create more strings. So we don't want to do that, right? Frequent reassignment of a string doesn't mutate the string, it just creates a new string. Not using symbolic constants, and this is one that people do a lot, right? When I put Steve as a literal constant, which means that I have like Steve actually in the method call, instead of Steve as a symbolic constant, which means that it sits up at the top and it's only created once, I create the opportunity for my code to create multiple copies of Steve, right? It doesn't know that there's only one Steve and it never changes, right? So, and shout out to all the Steves in the audience. And the last one is formatting. So every language does this different, but there is an optimal way to format your strings, and there is a suboptimal way to format your strings. Understanding which one to use when is really important. So we need to give a little love and care to our strings. Use a string builder, as I said. Avoid creating unique strings in a high volume method. And what I mean by this is really like, just if you know something is going to be high volume, just don't even use strings, right? Like it's just, strings are things that people should see. They're not things that computers should have to understand. So a lot of times when we use strings to mean something, we probably could or should do it another way. If you have to use strings, try to move it out of that high volume method if at all possible. And to that point, don't use strings to convey unique data. And be aware of the impact. This is a really important one, and we get to this when we talk about logging. Again, there's symmetry. A lot of people don't understand how much string manipulation in logging impacts their code, right? If I have a log debug statement and I know I'm going into production and I'm only going to take warning, guess what? All that string stuff you do in the log debug still happens, right? So be very careful. There are ways around this. You know, a lot of logging frameworks give you ways around this, but they are in the high mental load section, so we'll talk about that. Do we have questions on strings? Okay. All right, so null is never your friend. I was going to say never not your friend or something else. This whole section I basically wrote while I was listening to Tony Hoare, who is the guy responsible for creating null. If it wasn't him, it was going to be somebody else, but it was him, so you know, he talks about this. Null is a pointer, just like we have pointers for objects, except it's just parked in a particular memory location that means null. Everything that's set to null points to that same memory location. From his perspective, it was just a way to solve a problem. He didn't spend a lot of time thinking about it, and the consequences of that decision is what he calls the billion-dollar mistake. And what he means by that, and what I agree with him on, is that null references cause us to write a lot of extra code. It causes us to have to really reason about things that we shouldn't have to reason about, right? Null has no other intrinsic value besides it's just not pointing at anything, right? So when you return a null, right, you might know what it means, but you know, 12 methods up the stack, they don't, right? Null doesn't carry with it any other value besides this, there's nothing there, right? So because of that, our code is harder to reason about over time, and it's harder to reason about over distance. And so we really like, I've learned this, and this is a .NET thing, since they've introduced the ability to yell at me every time I am not thinking about null, right? So, as I said, null lacks any semantic meaning, which is problematic because it doesn't convey what is there, right? If I have a value, let's say name, and the name is null, that doesn't tell me what I should be doing with that name, right? It doesn't tell me if the name just simply wasn't provided because it was optional, or the name isn't there because of some data issue, or there are any number of reasons why name could be null, but the only thing I know is that it's null. It also requires you to check for it all over the place, right? Like before I do anything, if it might be null, I need to check. And if I forget to check, the one time I forget to check, it's gonna blow up in production. So different languages offer different things that can help you with this. I don't know how much it helps, but the difference between null and undefined in Java is marginal. You have structs, which will never be null, but they will just be full of default values if you don't actually initialize it. Compile time null checking. This is what I'm talking about, like with .NET. It'll just yell at you if you haven't dealt with null already. And then this last one, which I'm going to show you a little bit of, is discriminated unions. And again, the functional people are going to sit on their high mountain and feel superior. But a discriminated union is all about pattern matching, right? And it's actually really cool, and I really love it. And I'm sad that I would have to use F# to take advantage of it, because I'm never going to use F# in production. Okay, so traditional. This is pseudocode. This may look familiar. This is just a book. I call it bookshelf, but it's just basically a repository. I pass it an ID, and I get a book, right? And so I go to the database. I look for the book by ID. If it's not there, I'm going to return null. Otherwise, I return the book, right? So in this simple example, it's pretty straightforward. If it's null, then I'm going to print book not found. If it's not null, then I'm going to print, if it's not null, I'll print book found, right? That makes sense. But what about in your spaghetti monolith where the book gets pulled from the repository, and somewhere else in some code that is 10 years older than the code you're writing now, you've got a null book and you don't know why, right? So what a discriminated union does is it says, okay, look, this get book function is going to return two things. It's going to return either a no book or a book. So now when it can't find the book in the database, it returns no book, and otherwise it returns book. So in this case, it's clear, right? We have either a no book or a book, and I can write code that says what to do if it's in either of these cases, right? It's not uncommon that you have 3 or 4 cases to return null, right? So this helps to disambiguate that. And then in C# we have a framework called oneof that lets us get close to this, right? It's not built into the language, so it looks a little wonky, but we do have the ability to say, okay, well, this returns one of a book or no book. So null is less, I told you I wasn't going to say best practices, then I did. All right. Null is less than best practices. So we should use what the language brings. Every language is going to give us a different way to solve this problem of nulls, or at least it should. And we should make sure that we are taking advantage of those. We should always check for nulls at system boundaries and then avoid them internally. And what I mean by that is when you get a message coming in, or on the other end, if you're getting something from something external, in both of those cases, you should check for null. And you should then basically unit test the rest of your code to assume that if something's not supposed to be null internal to your code, it's not. Don't write null checks in every method throughout your code. That's just too much. We should interrogate and remediate every line of code that returns null. And what I mean by this is we should be asking ourselves, is there an alternative? Sometimes there isn't, but if there is, we should consider it. And we should assign default objects, and I've got an example next in case you wonder what I'm talking about. This is, again, I felt like a genius when I thought of this, right? I'm like, oh, what we could do is, and then I went and did some research, and I found out that Martin Fowler wrote about it 10 years before I. So let's talk about this null object pattern. So a null object pattern is basically a placeholder, right? What it says is I've created this thing, right? In this case, I've created this bookshelf. And some of you already are hating me because I called it iBookshelf. That's what we do. But if I haven't initialized it yet, right? Like I don't have the database, there's a reason that I can't use this bookshelf. I should be able to put default behavior into this bookshelf, right? So that instead of creating this iBookshelf and checking to see if it's null, and putting a whole bunch of like, if null, then skip it. If not null, then call the bookshelf and do these things. I insert default behavior that allows the code to continue to operate properly, regardless of whether or not it has been initialized with a real value or this null value, right? So it's sort of like a stand-in. And this can clean up your code a lot, because now you're not having to check if the state and behavior on this thing is there yet, right? This works in certain scenarios. It doesn't work in every scenario, so don't go like replacing all of your things with null object patterns as their initialized default value. But in the cases that it works, it's actually a really elegant solution. So that's nulls. Any questions on that one? Oh, go ahead. In Java, would a good alternative be optional? Does that let the compiler yell at you? Okay. Yeah, I mean, look, yeah, I'm a fan of static code analysis, and I'm a fan of static code analysis being part of your development experience. I know all you Java guys have been using, what is it, the JetBrains IDE for a long time. Yeah, IntelliJ, which is one of the best, if not the best. So I'm sure that it yells at you anyways. Okay, yeah, so it does complain if you ask about optional if it's present. Yeah, I mean, I guess, you know, it's like I said, every language brings something that you should think about using. Did we have other questions, or? Okay. All right, time. And speaking of time, we got time. We're doing good. I'm proud of myself. All right, time is the enemy. Any of you who have spent any time with me know that I have this super annoying habit of coming up with song lyrics for every situation. So time is, in fact, a piece of wax falling on a termite who is choking on the splinters. All right, so time is not on my side. So I have a few examples of how we can express time, or how time actually imposes itself on us. Let's put it this way. One of them is an actual concept of time. The rest are human inventions, right? But there's some problems that come with all of them, or things to think about, right? So we have an instant of time. An instant of time is basically like right now, right? And it should be the same for all of us. The problem is it's not, right? There's two reasons it's not. There is no such thing as a shared present. Any of you physics wonks will know what I'm talking about. But even the best network clock algorithms have to account for some amount of skew, right? And in addition, relativity actually is a problem that we have to think about when it comes to time. Your GPS, right, which works for you every day, actually has to account for the time, or account for the fact that the clock on the satellite ticks at a different rate than the clock on your phone. So these things, right, like there is no instant in time that we all share, right? So we can only approximate that and then use that in our systems. We have an instance of time at a specific place, right? So like right now in the AMC Easton 30 Theater 14 in Columbus, Ohio, right? And then we have an instant of time in a specific time zone. You know, right now in Eastern Daylight, we're in daylight, right? Eastern Daylight Time. An instant in time is an offset of UTC, which is a daytime with offset. And then we have a concept of time, or conceptual time. And this is the one that really kills me. Anybody who has had to write something involving time to a specification written by a BA or written by one of our, our product owners knows that how we talk about time is really, really squishy, right? And it's really, really squishy because we rely on our intuition, right? We don't think a lot about time because it just happens to us, right? If I, we all sort of share this experience about time, and so we don't have a really good language to express it. And because of that, it makes it really hard to translate what somebody's thinking in their head into what we can build in a system. And on top of that, and I will pick on .NET right now, the structures that most runtimes or frameworks or SDKs give us to deal with time are terrible, right? They're just awful. They don't even encourage us to think about this in any way, right? Like basically it's like, if you want to get it wrong, fine, I don't care. And time zones are political, right? Like, and you're thinking like I'm talking global politics. I'm talking about like the state of Indiana, or if you guys have seen it, the donut time zones in Arizona, right? And they change. So they're not always the same. If I am talking about Eastern time in Western Indiana, 50 years ago versus Eastern time in Western, well, no, they're not on Eastern time anymore, right? So they change, and they often change based on political affiliation, not really anything else, right? And there are cultural differences, and I'll kind of get to this in the next slide, when it comes to how we even express time. So does anybody really know what time it is? So commissions are paid every Thursday, right? What do you mean? What time zone are we talking about, right? Is it UTC? Is the head office time zone? Employees time zone? If you tell me it's 1, I'm probably going to say, well, but then that's not Thursday if you're here, right? So, here we have a very conceptual, easy to reason about thing. Commissions are paid on Thursday, which could easily, and this is a real example that I've actually had to deal with, turn into, I don't know, like 10 different 2-hour meetings. That occurs daily at exactly 4:45 a.m. EST. So the problem with that is, again, time zones change. They're political. Not only that, but when we say EST, it's super frustrating to me because it could mean Eastern Standard Time, which is basically what we're on when we're not on Eastern Daylight Time. But EST can also mean just basically Eastern Time, and you take Standard or Daylight depending on which one it is, right? First commit wins. So I was talking about clock skew, right, and the speed of light. Google has a product called Cloud Spanner. And Cloud Spanner is supposed to be actually strongly consistent on global scale commits. And the way that they have to do that is they actually position GPS all over their data centers because they can't rely on network synchronization algorithms in order to ensure that the first one actually is properly recorded, right? Because clock skew throws all of that out the window. That transaction happened at 121 minus 700. I know some of you probably love offsets. I think offsets are completely useless, right? For the reasons that we kind of talked about in this previous slide. What is it? Yeah, here, right? An offset doesn't even tell me what time zone it's in, right? If I try to do math on an offset time, the only thing I will be able to produce is what that time was in UTC, right? And in fact, doing the same thing in time zones also has a similar problem, but at least that is a little bit more stable, right? Because time zones will help me account for daylight saving time. Really, the only thing to do is to record the geographic position of where it occurred if you want to do proper math on time. And this is, again, another real problem that I've had to deal with. And then the final one, my wife, oh, by the way, that picture of me and my wife in the beginning, she doesn't know she's in this presentation, so if you can all keep that on the down low, I'd appreciate it. She's Vietnamese, and in Vietnam, when you're born, you're 1. And you age, you basically get to count the next year when Chinese New Year starts. So if you're born 2 days before Chinese New Year, when you're 3 days old, you're 2 years. So if I say, they can create an account when they turn 13, by whose rules? All right. So, we're waiting for someone to show you the way, and that's me. Within systems, we really should, I'm a fan of using epoch time, right? Epoch time is a number, not a string, which means that it's faster to sort, it's faster to search and range. You can do it with string, but like if you're able to, just use epoch time. If not, at least use UTC and use the round trip version of UTC, right? The round trip version of UTC is sortable. It goes year, month, day, hour, 24-hour format, hour, minute, second, and then 7 fractional seconds, and then the letter Z. So time zones, as I mentioned, actually time zones should be a localization concern. Please, if you can, just let the UI take care of that, right? And if you need to store information about time zone, first of all, don't make it the offset. It doesn't really give anything useful. But store it adjacent to the time, right? Like, don't store it as part of the time data, because that just ruins the ability to actually use that data for anything besides actually looking at it with your eyeballs. And don't underestimate the complexity of dealing with time in your designs. If somebody is giving you a feature that involves time, stop and take a minute to think about exactly what you're missing when you're just intuitively understanding what they're saying. Any questions on time? Okay. Last one is logging and logging and logging. So why do we log? We log to troubleshoot a specific issue. You know, hey, the code's not working and it's in production. What do we do? Well, let's do an emergency patch with a bunch of logging statements in it. To capture context for inspection, so you know, we need to see what was in the request payload. So let's just capture that at the beginning of every request. Trace a request across services. So, you know, how do I see what's happening across services? Build metrics after the fact. So what I mean by this is you get into production and you realize that you have no visibility into what's happening into the system. And it takes too long to get that from the logs. So you write some queries and then you put a graph around it and you're done. And then we log that one error that in every method in the stack. And that's that catch log throw that I mentioned earlier. So what are we supposed to do? Well, we're supposed to have a plan, right? Like, and I know logging, it just really isn't that exciting, but we should have a plan, right? Like, how do we consistently do this at the right level of granularity that we're getting the most out of our logs? Not profusely, right? So having a plan doesn't mean doing a lot of logging. It means doing the right amount of logging. Don't log errors reflexively. You know, when I talked about exceptions, I kind of mentioned this. I might have glossed over it a little bit. Like, the only time you should log an exception is when you don't know what else to do with it, right? And that should be your last chance, right? That should be your exception handler that's sitting right above your app.run, right? So you don't really need to log it everywhere, right? Like, the stack trace will take care of that for you. Think about performance. And I mentioned this before, but I'll go a little more into depth here. If I'm sending strings into a log statement, that string gets allocated even if the log statement doesn't get recorded, right? Some frameworks will give you a way to work around this. In a lot of cases, they're not intuitive. So, you know, look for the best solution available in the language that you use. The one that I use is C#, and I've been very happy. They introduced code time source generation, which is really great because now I can actually take advantage of all those optimizations by just creating classes, and then it like magically does this stuff behind the scene. Use log context rather than formatted log message. So really, when I look at logs, I have a really hard time. I don't have a visual memory, so I have a really hard time scanning logs. The message shouldn't be context specific. It should be log specific, right? So if I'm logging a thing, the message shouldn't have like all of the details in that thing. They should be in the context of the log itself. And what I mean by that, and this is a little harder when you're doing console logging, but what I mean by that is that you can inject context into the log as contextual data, right, as properties. And then the message itself, the text part, is really just what you can use for pattern recognition when you're scanning through your logs. And to that point, event IDs are actually better than the message. if you have the ability to use event IDs, use event IDs, right? And they don't have to have any rhyme or reason. I like for my event IDs, I usually just hash the method signature, and then add whatever I want to it, and that like weird long number ends up being my event ID. But it allows you to classify. It allows you to better filter your logs, and if you want to do counts against them, it's much easier to do than scanning for bits of text inside of your log statements. It's also cheaper in the long run. And actually, in the terms of managing counting things and cheaper, if you have custom metrics available, use them, right? I've been personally guilty as well of writing a lot of complex queries around my logs, and then at the end just doing like count and then feeding it into a graph and being like, okay, we got a dashboard. Think about it, right? Like spend some time putting some energy into understanding how you measure your system and build those as custom metrics instead of as post facto queries against your logs. And then the final thing, the last thing, actually I added another slide at the last minute, so it's not the last one. Traces and spans are great. Don't use your logs to build them, right? If you're not using a logging framework that supports this, go find one that does. If you're not using a logging website or provider or whatever that doesn't provide this, go find one that does, right? Because this is how you are going to be able to visualize what is happening inside of your system, right? Traces are this is called a flame chart. Traces are the vertical part of the flame chart, which helps you understand the relationship in ascendancy between service or between class or whatever it is within your system. And then the horizontal component is time, which helps you understand where your bottlenecks are, right? So they're very important. And the great thing is, if you are using a product, a lot of them actually will have the ability within modern languages to weave that in for free. Not for, there's a little bit of a performance cost, but basically for free. And then that leads me to this last slide, which is if you're not using an APM package, it's a really good idea, right? Because like a lot of the stuff that I've talked about here just gets taken care of for you, and you can focus on writing the code. If you have the ability, a lot of times you just drop it into your container and it takes over, and it's happy days. So any questions on logging? All right, well then this is our final slide, the conclusion. And I don't know if you guys were paying attention to the generated images, but this one was particularly fun, so I thought I'd highlight it at the end. I'll bring you back to what I said at the beginning. Oh, and by the way, this is that route up there, m.eado.ws/s/23/StirTrek, is where you can find the blog post for this, which will link to the slides at the bottom. I've got to work on the styling a little bit because the text in the link is yellow and the background is white, so I apologize about that. But everything that I've said here is important, but like don't start there, right? Like go there. Over time, if you kind of learn how to deal with these things, it gets easier. But like, don't sit down and think, well, I'm going to do all of these things, right? Because you're just never going to get anything done, and your code's probably still going to suck just in other ways. So that's the end of the presentation. Do we have questions or any on Discord? No? All right. Well, how did we do on time? A little bit under. Look at that. Yeah, I was doing like 10 minutes late when I was doing a walkthrough, so we hit it. All right, well, thanks for attending.